Thanks again for having me. I know it's been a fun year over here at Venus, and so I wanted to give a couple of fun updates. The big one, we flew our supersonic drone that's shown on top. I'll show a nice video of that. Some significant progress, as Sunny mentioned, on the rotating detonation engine, the kind of highest thrust picture we have so far down on the bottom. And then I'm also going to reveal some of our testing we did in the fall and had a really major discovery that's kind of completely shifting how we're thinking about the detonation engine in application to high-speed flight. And certainly I appreciate y'all having me here as the slowest moving dreamer. I'm only talking about, hypersonics, none anything faster than that. So much appreciated for being here. So, the funny thing about hypersonics is that people tend to think that it's new. It's been a really interesting journey for us as, the use of hypersonic weapons has sort of got people talking about hypersonics, but really it's no. Hypersonics are actually quite old. And so, here was the first vehicle to go hypersonic, and it was the X-15 powered by a rocket engine, of course. And then if, space shuttle for many, many years did much faster and much higher. And so, this is really, when we think about commercial hypersonics, we're talking about not doing something new, just trying to do it more efficiently. And so I have, my favorite Enzo Ferrari quote here, which is, aerodynamics for people who can't build engines. So really, this is an engine challenge primarily, and that's how we're looking at Venus to kind of use the rotating detonation engine to change this as a big shift. Of course, hopefully everybody here has seen Top Gun Maverick. That opening scene was awesome, but it also really helped highlight some of the challenges of hypersonics. Namely, when you go fast, it gets really hot. Now, unlike the movies, if you eject at Mach 10, you don't just need a glass of water when you're done. That's a pretty harsh ejection at Mach 10. But nevertheless, that was a pretty exciting to see hypersonics kind of highlighted in movies. And so, I want to frame a little bit when we talk about engines, just as a sort of highlight, usually you're looking at, and from an air breathing point of view, a couple different configurations. So you have a turbojet engine where, the old thermodynamics, suck, squeeze, bang, blow, you're drawing in air, you're compressing it, combusting it, and then sending it out the back, and of course, extracting a little bit of work from the turbine to power that compression. In ramjet, you are using some of the forward velocity of the aircraft through compression waves to generate your compression, and then burning subsonically, and then exiting out the back. And then in scramjet, you're actually still shocking the air, but to higher pressures, but you're going to leave it supersonic, because at a certain amount of speeds, that bringing the air all the way to subsonic is crazy, crazy hot. Not only a materials challenge, but just trying to add energy once the air is already at a very hot temperature is very challenging. So I want to show you some videos of kind of some of our progress, and I'm going to kind of come back to this and then highlight what we're now thinking with the detonation engine, kind of a new discovery that we made in the fall. And so, man, all the videos played at once. Hang on. Stop, stop, stop. All right. On the top, this is our highest thrust detonation engine yet. It's about 2,000 pounds of thrust. This is jet fuel and hydrogen peroxide. And, the combustion's happening in an angular ring. In fact, this is kind of a high-speed video of what's happening. And so you have detonation waves that are standing up. Detonation is just supersonic combustion. And by doing this, we are actually, combusting closer to constant volume combustion. So you actually end up getting a pressure gain, which is helpful. If you think of a rocket plume and you look at all that thermal energy that was sort of left on the table, it was the plume was hotter on the inside of the rocket engine, but it was at higher pressure, and used through pressure, you converted some of that into thrust, but certainly not all of that energy. And so combusting with rotating detonation allows us to have a slightly higher pressure gain and then a little bit more thrust on the end. So certainly from a pure rocket point of view, detonation engines technology is very exciting, and we're happy to have really progressed it quite a lot this year. In fact, on the bottom left, this was from our fall testing, and this is now sort of a long duration. And so, big technical challenge here is that there is a lot more heat being generated through the detonations, and this is us, demonstrating that we've solved the heating, the cooling problem with the engine. So kind of a long duration run of the detonation. And then our really interesting discovery, we decided to run an experiment where we combined this with air, right? So since we were looking at hypersonic flight and not, flight into the vacuum of space, we certainly are flying the whole time, all the vehicles we're thinking about making. And so we wanted to see, could we harness the air and then with the detonation engine, mix the rocket exhaust with the air? And that was this experiment on the bottom right. And forgive the water, that was just a cheap way to keep the duct from not melting. So we can go run that experiment. And this represents about a Mach 2 condition where the detonation engine mixes with the air in a very quick amount of time. It's an old idea called rocket-based combined cycle, but it sort of stalled out with just how long the rocket plume, and any kind of rocket plume you would put in front of a ramjet was so long that it wasn't feasible from a vehicle configuration point of view. So the rotating detonation engine really changes that. And so this was an experiment we ran in the fall, and boy, it's really changing the way how we think about using the detonation engine. And so, what we're going to go try and build over the next year is certainly we're going to build something that looks kind of like this, and where we have an aero spike on the front to do the shockwave compressions, and then we'll put our RDRE just behind that, and so that we can kind of add pressure and heat to this incoming air, and you'll see it mixed there. And that'll let us actually start the ramjet really early. So normally ramjets need to get to like Mach 3.25, maybe Mach 3.5 to start. This will allow us to start the ramjet pretty early. I'm working with a company out of Cincinnati called Volantra to go do this. So this is kind of our new concept. Like I said, the kind of a major discovery for us in the fall. And honestly, this brings the timeline for flight for us way in. If you remember last year, we were talking about using the detonation engine only and kind of doing more of a boost glide formulation. This really lets us aim for kind of cruise ranges around Mach 4 to 6. And so this little video just kind of show what's happening. And so, this is from one runway to take off all the way up to Mach 4 to Mach 6. And so at first you have the detonation engine, which is providing the thrust. As you get up to altitude, the thrust will get a little bit better with the rocket plume, a little bit better expansion. And then what we're going to show here in the video is once we go supersonic, we're going to light the ramjet that's kind of behind here. And so as the shockwave stands up, we have the right amount of pressure and temperature condition to then light the ramjet. Now the ramjet's on. And then jumping forward, at Mach 2.5, we'll actually start throttling back the detonation engine. We now have enough compression from the air that the ramjet doesn't need all that much extra help. And then by about Mach 3.5, you see there, we've completely turned off the detonation engine. Since I know we have some engineers and scientists on the call, I wanted to put down kind of our modeling in terms of what does it look like from a specific impulse point of view. And so certainly this is, a way to achieve ramjet conditions. And certainly the sort of the old idea to have a reusable vehicle achieve ramjet conditions would be using a turbojet, which has its own kind of thermal problems. And there's kind of a gap there between where you can start the ramjet and where the turbojet will get you. So this is our new idea. And to kind of show where this then allows us to sit, is we are able to fly at higher altitudes. This is a plot of speed versus altitude. And I really want to highlight where, if you're trying to be a fast flying jet where you have to fly low enough to have, enough air for your jet engine as well as that ramp start, you're going to be in this kind of gray zone here where it's going to be pretty hot. And so there are companies out there trying to chase that technology stack. It's really, really hot. Whereas if you look at sort of where the SR-71 flew, and of course, range of where the X-15 flew, we have data from where this looks like. But, our idea is to fly at an altitude that's a little higher up where, titanium is good enough from a skin temperature point of view. And, but certainly enough air for our ramjet to go. So that's what we're looking at doing. And, because no one will believe your engine until it flies, we're also been on the side building drones. And this is our flight. Pause here and describe this as a supersonic drone. It's about 8 foot long. It was powered by just hydrogen peroxide thruster. So our detonation engine is using peroxide and jet fuel. So we decided to make a very simple drone with just one leg of that combustion process. And although it's capable of supersonic flight, we didn't have regulatory approval yet. So this was actually a flight where we went Mach 0.9, and that happened in February. And while we're not doing any innovations on sort of, avionics or flight controls or structures, any of that stuff, it's still a thing to go make it and do it. And so this was our sort of first drone. And so over the next year, we're going to kind of piece it all together into a larger drone that can go Mach 4 to Mach 6. And this is kind of our new configuration of what this would look like as a RDRE ramjet powered vehicle. And so something more along the lines of Mach 4, so not necessarily having to use a wave rider at those speeds. And, we are still chasing that commercial market. Of course, there are other markets before then, but this is kind of our North Star. So over the next year, what you're going to see us do is take our detonation engine, combine it with a ramjet, put it onto a new drone. It'll have a little bit larger wings than the current drone. And we're going to need to use new carrier aircraft. So, all right, we're thinking about a MiG, but there's other things that might work for that as well. So that's kind of our path over the next year is we'll fly a detonation engine on the wing of our L-29. That's the aircraft here in the middle, the black aircraft. So sort of first, flight, it'll provide some thrust, not too much. And then we'll do a drop test of the new drone vehicle by the end of the year, and then get into powered flight next year, and then on to ramjet powered flight after that. So that's our path, and glad to be here with you guys and share kind of some exciting updates on our end.
Hey, thank you, Andrew. This was great. Really appreciate that. I got just a few more minutes. I got a question that came in because I know you got to probably duck out a little bit before too long. Question just came in from Ryan Weed. He was curious about the partnership with Volantra.
Yeah.
Is there a turbo machinery path from Mach 0 to Mach 6 in the near future?
No, so the work we've done with Volantra so far, we did have them looking at a turbo machinery combination. And then with this new discovery of the detonation driven portion of this, we're just going to have our detonation engine drive directly into the ramjet. The nice part there is, if you look at a full vehicle configuration, normally a jet engine might weigh about 10% of the mass of the vehicle. And so if you kind of do all the math, certainly I'm going to go back to this graph here. So certainly a turbofan would use less fuel to get up to speed, right? They've got higher specific impulse. We'll use more fuel, but boy, once we're at top speed, we don't have this big dry hulk of a mass that we have to carry. And so, in fact, we already kind of win. I'd rather take that extra 10% as fuel. We won't use nearly that much to get up to speed. And then the second part of that, and I kind of highlight a little bit here, once you're flying supersonically, the drag goes like volume squared. And so, depending how big that jet engine is, you could see vehicles that might have 20, 30% extra drag, and that really stacks up. And so, our best estimates would be that our range, if you can get rid of the jet engine entirely, that our range would go up by, 30 to 50% compared to a turbine-based combined cycle.
Okay. Yeah, very good. Do any of our performers have questions?
Yeah, this is Charles. Hey, Andrew, thanks for sharing all your great progress on detonation engines. I was just wondering about the acoustics and if that's still an issue, or how are the acoustics?
Yeah, that's a great question. When we ran this test here, in the bottom right, stop. We were really surprised how quiet it was, kind of buried inside of that duct. And so, we'll take a look at it as we kind of stack up the full engine and see. But yeah, from a commercial point of view, that would be one of the limiting things. If the acoustics are still really loud, then that would be a barrier to take off. And you might find yourself back in the world of attaching a small turbine. Yeah, great question.
Yeah, do the acoustics introduce any sort of material issues or forces that you have to worry about?
No, the only, compared to a rocket engine, the interesting thing with the detonation is you actually really hear, the waves are going around about 10,000 times per second. You actually hear those overtones. So we can actually hear, I mean, sitting in my office here, because we're just testing outside on the other side of our hangar, I can hear if we actually got to detonation or if it was just a deflagration, depending on that test. There's a whistle that shows up. That's pretty fun to hear.
Oh, cool. Thank you.
Great question from the guy that was in charge of advanced R&D at Skunkworks.
Yeah, we looked at detonation engines for a long time and tried to integrate them in, and
Yeah.
they were never quite ready.
Yep. Yeah, that's
Yeah,
right.
yeah,
Yeah, absolutely. Yeah. That was really my story because I was at Virgin Orbit before all of this, and I saw finally the right level of progress kind of 2018, 2019 out of academia, and I said, man, here it is.
right.
It's now getting close enough that someone should go try and raise a whole bunch of money and pull it forward. So yeah,
Yeah, and getting the turbojet up to the speed where the ramjet can take over, that's not an easy thing there. That whole,
that's right.
right. Yeah.
That's right. Yeah, there's a big gap there between where the turbojet sort of want where it can get to and where the ramjet wants to start. Yeah,
Yep, yep.
absolutely.
Great solution. Really good work. Thank you.
Thanks. Thanks.
Yeah, this is exciting, Andrew. We're really excited for what you guys are doing. Thank you for the update. Thank you for giving us some of your time today. So
Yeah.
really, really do appreciate that. Definitely good luck in everything you do moving forward. I know you'll keep me well informed since you and we're always doing stuff together. So
Yeah, you bet. Thanks, Sonny.